All right, welcome everybody. Monday, 5 p.m. So we've completed chapter 3 last week, Wednesday, on Kinematics Wednesday. Before we move on to 2D, I want to make sure everybody is on track. And so based on the lectures we've seen, the corresponding book chapters, reading, and based on the problems that you must have completed by now, is there any one of them that cause problems? Is there any question that you may have on any of those problems, such that we'll make sure that everybody is comfortable with 1D before moving to 2D? Any questions? Okay, so I will assume everybody's on track, everybody's good on vectors, section N and D, and one question, problem 8. Okay. Problem 8 on kinematic 1D. All right, so let's do number 8, free fall. We are being told that a stone is being dropped and is being confirmed with a parenthesis. So the keyword obviously is dropped, which again is confirmed by no initial speed. That tells us right away that V naught is equal to 0. Let's write them down on the corner. It's being dropped from the top of a pine tree. So from here. If it's going to be dropped, we know the trajectory of this stone is going to go straight down. All right. It will strike the ground in 3 seconds. So we're given the time between the initial point and the final point of t is equal to 3 seconds. All right. So those are two given quantities. And the question is, how tall is the tree? So, how are we going to deal with this problem? What is the first step that we want to use? Let me bust up the usual equation. Brian, how did you start it? Where did you get stuck? Did you get stuck on the first part, the second part, third part? Okay, so before we determine which equation to use, we have to simplify them. So let's go through each step at a time like we did last time. And again, remember, if you're non-WI, you're welcome to follow the steps so that you can get partial credits. And if you're in a WI section, you're going to be required to follow those exact same steps. So, first thing for kinematic type of problem, we first draw a clear diagram. We've just done this. And we pick a coordinate system. So which coordinate system would you like to pick, and where would you like to put its origin? Okay, where you'd like to put the y-axis? Horizontally, vertically, pointing up, pointing down, with an angle. Ground as the origin, okay. So that takes care of the x-axis. And y vertical, okay. Now you want vertical such that positive y is up or positive y is down. Okay. So this is the coordinate system that we're going to use. Perfect. It is obviously a free-fall problem. Therefore, which equation can we simplify right off the bat? Excellent. First one goes away. Perfect. The motion is taking place in the vertical direction, and therefore along our chosen y-axis. Therefore, what will happen to all our equations? Excellent. Thank you, Cynthia. Thank you, Brian. So all our y are going to become x. I'm sorry, all our x are going to become y. Perfect. Now, this is also, again, a free-fall problem. Therefore, by definition, we know that the acceleration is constant, equal to 9.81 meters per second squared, and its direction is down. Based on the fact that we've chosen positive y to be up, what is the consequences of this on our equation? Excellent. Can you be a little bit more specific, Cynthia? Where and which term in those equations do we have to change the sign? Excellent. On the acceleration. Now be careful. It is not gravity. A is the acceleration due to gravity. Gravity is nowhere in those equations. Gravity is a force. We're going to see that in Newton chapter. Right now, we're only concerned about the acceleration, A. And if we're dealing with a free fall problem, this A happens to be called the acceleration due to gravity. And we will see later on in Newton's chapter that is because the only force acting on our system is the force of gravity, which we'll call weight. All right. Perfect. Okay. What else? The last thing is, what does the location of our origin tells us? Specifically, is there any simplification that we can make on those equations due to the choice of having chosen the origin at ground level? We'll get there, Joinar. But before we get to the meaning of drop, what about investigating the meaning of or the consequence of positioning the origin at ground level? Is this going to influence our equations? Nope. Remember, we talked about this last time. What is the consequence of the origin location? Does it affect position, velocity, or acceleration? Position. Excellent. So, if we chose the origin to be at ground level, is our y not affected, and how? That is it going to be 0? Excellent, Cynthia. Obviously, it's not 0, right? Because at initial time, we're here. Therefore, at initial time, the initial position is located at this distance from the x-axis. Therefore, we cannot simplify y naught. So we're going to keep it as it is. But we know that as we're looking for information right here at ground level, this will be when our y is equal to 0. Good. Last one. Let's look at what's given to us in the problem. We're given the time it takes to go from this point to this point, no problem. And as Jominor was suggesting, we know that the keyword was present and specifically said dropped. Therefore, we know that V naught is 0. Hence, we can simplify our equation one more and nuke all the V naught. Perfect. That's it. Let's rewrite those three equations so it's nice and clean. Y is equal to y naught minus, and here it's your choice. If you decide to keep A, keep A. Since you, whoa, what just happened here? Or you may want to replace it by G, by the convention. Oh, here we go. GD squared. The second one is V is equal to negative AT or GT. And the last one is V squared is equal to negative 2G y minus y naught. Did you get those simplified equations, Brian? So did you get to the same step as we are right now? Excellent. So if we had chosen to put the origin at the top of the tree, that's where our x-axis will be. Those equations will be a little bit different in the sense that all the y naughts will be 0. Okay? That's the only difference. All right. So the question is, how tall is the tree? So how tall? What does how tall refers to? Does it refers to which variable? G, T, Y, why not V? Y. Excellent. So we're looking for a change of position because it's how tall. Therefore, it's concerned Y minus Y naught. All right. So obviously, since we're looking for how tall this tree is, we want to apply any of those three equations between point A and point B. Those refers to the 2 points that delimit the height of the tree. So, which equation has position involved, since we're looking for positions, or how tall? Are we going to use the first one, the second one, or the third one? First one, excellent. First one has everything that we need. He has G, which is known. He has T, which is known. And therefore, we're going to look for Y minus Y naught. All right. And remember, this equation is applied between 2 points, A and B. A refers to the variables that have a knot, and B refers to the variable that doesn't have a knot. Based on this, what value, and we're looking for Y. So what value are we going to put, or why not? So what value are we going to put for all those little buggers? Are you going to solve for Y, or are you going to solve for Y not? Or which one of the two do we know? Excellent. You're going to solve for Y not, because we know where Y is. How do we know where Y is? If you apply the first equation between A and B refers to the variables that don't have a knot. Yeah, excellent. At B, our position is 0. And since we apply this equation between A and B, A between a knot, B none of knot, this Y refers to the position at point B, which from our diagram, because we drew it along with the coordinate system, tells us right away, this is 0. Therefore, we have a 0 here. And Y naught is what we're going to solve for, which refers to the position at point A, which is nothing else but the height of the tree. Okay? Y naught minus 1/2 9.81 times 3 squared. Oh, so remember, all those equations are always applied between 2 points. So you have to be very, very clear which 2 points you're applying every one of those equations with. So I would draw them. So I put my first point here at A, which is my starting point, and B, my ending point. So B is the point right before it hits the ground. I want to choose those 2 points because A is what I'm looking for. And based on the choice of our coordinate system, A refers to the initial position, therefore Y naught. So just by looking at the diagram and the location of the coordinate system, you have identified which is the one you're looking for. We're not looking for Y, we're looking for Y naught. If you had put the origin at A, we will be looking for Y, because Y naught would be 0. So now that we're looking for Y naught, we need to identify every other component. G is given, T is given, so we have to ask ourselves, what is Y? Since we are very clear that whatever the variable doesn't have any knots, it refers to the final point, which is B, then we have to ask ourselves, at point B, which is the instant right before the ground, what is its coordinate? Since B is located right on the x-axis, Y is 0. Does that make sense? Justin? Excellent. Now we solve for Y naught, and obviously this will be positive, whatever this number is. It got to be positive because Y naught is above the x-axis. Good. B, calculate the velocity of the stone right before it hits the ground. Okay, so based on the question of B, at which point are we calculating the velocity from our diagram? Is it the velocity of any of the points that we already used, or do we have to use the third point? If they ask for the velocity of the stone right before it hits the ground. Is it the velocity at point A? Is it the velocity at point B? Or is it the velocity somewhere else? I'm asking, which points are we calculating the velocity? Don't rush into using equations. That's usually where mistakes occur. Always ask yourself, at which point am I looking for a particular variable? And then deduce, okay, which are the 2 points that I'm going to use this equation? Unless you have answered the question, don't start picking equations. Statistically, you're going to get it wrong. Okay, so do we all agree that the velocity that we're looking for is the velocity at point B, which is right before it hits the ground? All right. Therefore, we're going to use point B as one of the 2 points. Obviously, we're still going to use point A, because now we know information about point A. We know its initial velocity, and now we know its height. Yep, B is at the ground. This is the ground. This is B. This is our x-axis. So, I'm guessing when people were saying third, you were referring to the third equation? Yes, we mentioned that last week. It's always going to be right before it hits the ground, because at the instant after it hits the ground, the velocity is 0, which means that it is not a free fall situation, because the force now that is acting on the object is a force from the ground. So in kinematics, whenever you put a point at ground level, either at initial or final, it's always the initial state, right before it's being shot, and right before it lands. Okay? So, third equation. Now give me all the variables that we know. If we're going to apply this equation between A and B, what are we looking for? Obviously, we're looking for V. That's the only V present. Can you give me the functional form of everything else? What are we going to put for G? Excellent. Always positive 9.8, Cynthia. Thank you. What are we going to put for Y? Oh yeah, 9.81. Y refers to the position of which point? A or B? Final or initial? If we go from A to B. Remember, if we go from A to B, initial is A, final is B. Y naught refers to A, initial. Y refers to B, final. Excellent. Wait. Y is equal to 0. I agree. Same as before. Y naught is not equal to 0. Otherwise, we would have nuked it here. Y naught is equal to this distance. This one. That was not 0, right? Yes. It's a common problem. So, excellent that you got it backwards now. So let's try to fix it so that it's become clear once and for all. Good. That's what we're here for. Fix any problem we may have. Do we all agree that this Y has to be 0? Because again, we are applying this equation between 2 points, A and B. We start at A, we end at B. If we start at A, it refers to all the not variable. So the only thing that refers to A is Y naught. Everything else, Y and V, must be referring to point B. All right. What are we going to put for Y naught? Anybody? Yeah, the initial height. Excellent. That's the one we just obtained. Oh, Michael, 9.8, 9.81, everything is good. Just don't use 10. If you use 10, yes. But between 9.8 and 9.81, I'm fine. So no worries. Good question. So, remember when we take the third equation, we have to be always very careful because it has a square. So if we're looking for the velocity, we have two solutions. Which solution do we have to keep? Because they ask for the velocity. Therefore, we have to provide not only its magnitude, but its direction. Excellent. We're going to keep the negative one. Thank you, Justin. And the reason for this is, let's just plot the velocity vector at point B. Obviously, it's down. Since we decided to have positive y up, naturally, every point at every instant of time after A will have a velocity vector which is always down. Based on our coordinate system, it gotta be negative. Therefore, we keep the negative guy. Excellent. Brian, is that good? Does that clarify? Perfect. Last one. Draw acceleration, draw the position versus t, velocity versus t, and acceleration versus t. Okay. Let's plot them one above the other. Time, 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 position, velocity, acceleration. So, based on your equation, and using what we've learned last Wednesday, what kind of function are we going to have on the position versus time? There's going to be a line, a polynomial of second degree, of third degree, or fourth degree, an exponential, or an logarithm, which you can also answer by looking at the equations. Is it going to be a line? Nope. Go back to what we done last Wednesday. We talked about this. Is this the equation of a line? Y as a function of time. So let's go back to Math 135. We need to make sure we master Math 135 and Math 140 for this class. Yeah, it's going to be a parabola. So make sure you take notes. It's always a parabola in free fall. Always, 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 because it's a polynomial of degree 2, because of time. Always. Now, what we mentioned last time, is it going to be a parabola that looks like a U or an inverted U? Eric mentioned it's an inverted U or N-shaped. How do you know that? Excellent, Cynthia. Excellent. Eric, back on parabola. Perfect. Yeah, because of that negative sign multiplying the highest factor. Excellent. So we know it's an N shape, excuse me, or inverted shape. Where are we going to start? On the y-axis. Are we going to start here? Are we going to start here? Are we going to start above, below, or right on the axis? Based on our equation. Above, excellent. Why? Because y naught is not 0. So when we start this process, we are obviously at point A, which is above. Therefore, we're going to start here. Now, the next question is, how are we going to draw that n? And for us to be able to answer that question is, we need to figure out the slope at t is equal to 0. Once we know the slope, we know how to translate our n shape. What is going to be the slope at t is equal to 0? And how do you know that? That is, are we going to start at the top of the n, or are we going to start somewhere down the leg of one of the legs of the n shape? Think calculus. V is dy dt. Therefore, v, the velocity, is the first derivative of position with respect to time, which means that graphically, the velocity is a slope. So what is the velocity at t is equal to 0? Excellent. It's right there. It's given to us. Therefore, we know the slope is 0. Therefore, we know that the n must be like this. We are the top. Perfect. Now let's go to the v versus time. Where are we going first? What kind of function are we going to use for velocity versus time? Again, look at your equation. Is this going to be a straight line? Is it going to be a parabola? Linear. Perfect. Now the next question, once we have identified it's a line, what about the slope? Is it going to be a zero slope, positive slope, or negative slope? Michael suggests negative slope. How do you know that? Yeah, right there, this negative sign. Perfect. So we know it's going to be a straight line like this. Now, where are we going to start? Are we going to start above the x-axis, on the x-axis, or below the x-axis as we plot this vertical straight line with a negative slope? Excellent. Again, we're going to use the fact that v naught is equal to 0, therefore we have to start here. Perfect. Excellent, excellent. And the value of this slope will be equal to if you look at the equation, or by definition of free fall, the value of this slope must be equal to excellent, negative g, right? Negative, which is right here. Y is equal to m times x. So again, basic algebra. So that's what we need to review. Perfect. Which implies that what must be the functional form of this graph? Because again, the acceleration is the first derivative of velocity with respect to time. Therefore, the acceleration must be equal to the slope. And since it's a line, the slope is always the same, negative g. Hence, what must be the function for an acceleration versus time? Is it going to be a straight line, a parabola? Dixon, I apologize, but I believe that such language is unacceptable. Hey, where'd he go? Who's that guy? Ah, he left. Good. I apologize, everybody. I will report it for sure. And hopefully this will not happen again. Okay, let's keep going. Yes, it is a line. What kind of line? Is it going to have a zero slope, a negative slope, or positive slope? That is, if you have a zero slope, that means the value is not changing. If it has a positive slope, that means its value will increase over time. If it has a negative slope, that means its value will decrease over time. So is the acceleration going to increase, decrease, or stay at the same value? Yeah, definition of free fall, right? We need to know of definition. Free fall tells us that the acceleration is constant. Therefore, we know that its value doesn't change. What is its value? 9.81. Since we put positive y up, then the functional form for A is a straight line with zero slope below the x-axis, which again can be obtained just from calculus, basic calculus 1. Derivative of this function will give you negative g. Similarly, the derivative of this function will give you this. So you can think in terms of calculus very easily to populate those kinematic diagram, or you can confirm or use the physics, either way. So very, very simple application of basic calculus 1. So if this is something very surprising to you, make sure you review your calculus 1. That's going to be fundamental for us. If this is a problem, but you feel confident with the physics, then that's perfectly fine as well. Either or. I would suggest you do both so that you always get confirmation of what you do. Any questions? Brian, did we clarify everything on this problem? Excellent. Any other questions? You mean below the x-axis? What do you mean by negative? Okay. Two reasons. First is, as we just did, look at the math. You know the basic definition of acceleration, which is dv dt. V is this. So just take the derivative, and you end up with that. Negative g, which means it's a straight line of power 0. At the same time, use the physics to confirm. Okay, what am I doing here? I'm doing a problem that is clearly a free fall. Okay, let's bust up the definition of free fall. Free fall tells us two things. That A is constant. That means it doesn't change. And its direction is down. Therefore, you expect A to be always constant. But just by this piece of information, you would expect it to be above. But then you look at your coordinate system, and this tells you, since the magnitude, since the direction of A is down, and you decided the positive y to be up, then this will come below. Does that make sense now? So you always have two ways to look at it. Excellent. So of course, as you can deduce and guess, if we had chosen y to be positive down, then all those signs for j will be positive. And therefore uv will be like this. uu will be like that. And acceleration will be positive. So if you are being asked for those on the test, if I don't see your coordinate system, you cannot get points, because your answer depends on the coordinate system. So keep that in mind. If you want credit for those kinematic graphs, you need to make sure that you indicate your coordinate system. And those functions have to be consistent with the choice of your coordinate system for you to get credits. Because as you've just realized, depending on which coordinate system you pick and which direction, all your equations will be different. And of course, therefore, all your graph will be different. Okay? Good. Any other questions? Another question from Michael. This one, okay, in the example for 2D kinematics, the example you were using reminded me a lot of Raymond's sum, and I was just wondering if there is an equation or it just looks similar. So can you be more precise about those examples? Which one are you referring to specifically? Is it from the lectures, or is it from the schedule, or is it from the homework page? The lectures. Are you referring to part A? And if so, A1, A2, A3, A4? Riemann sums. Are you suggesting that I've used Riemann sums in those lectures, or it just reminding you of Riemann sums? And if so, which lecture? Trying to think on top of my head where Riemann sum may show up. Did I actually use Riemann sums in any of those lectures, A1, A2, A3, or A4? Ah, okay. Oh, okay. So you're referring to something like this. Let's say we go in 2D. And then let's say we look at the velocity vector. Either here or here. And I've decomposed my velocity vector as in the vector chapter, section A and B, such that one is horizontal, the other one is vertical. Horizontal and vertical. Ah, okay, good. I can't think of any relationship with Riemann sums right now. However, I do see a clear application of the vector chapter, right? Section A and B, where we have any vector, in this case it would be V, that we have decomposed into two components, Vx and Vy. Vx and Vy, such that Vx is along the x-axis and Vy is along the y-axis, which allows us to identify the right angle triangle, which in turn allows us to use trig to obtain the functional form of the x component or the y component. But other than that, I'm not sure. If you're around and I haven't satisfied your curiosity and you may have something else that comes to mind, please email me or stop by my office and we can talk about this some more. Unless there is something else in those lectures that I have not addressed that you still have questions about with respect to possible correlation with Riemann sums. Or is it just the shape of Riemann sum that this reminds you? Ah, okay. So as far as I know, and I may be wrong, it may just be a coincidence so far. However, you're going to be able to make the nice analogy between Riemann sums and Newton's law. So yes, it will come. So if I may have mentioned Newton's law in those lectures, that's where you may have seen it. Absolutely. So that correlation will come. However, that doesn't imply that we're going to be dealing with series. Just sum, which is just adding a bunch of entities. Good. It is. That's why physics is so cool, because that's usually the first science class that we are subjected to where we really see how powerful the mathematics is, whether it's algebra, pre-calc, trig, or calculus. Excellent. Any other questions? So you've all completed all the problems on the course website. With respect to kinematics, right? Or the Kinematics 1D. All the lectures are understood, mastered. Make sure you pay special attention to those equations, because I may ask you that on the test. And then you've completed and mastered all those problems. Okay, good. So the last thing I want to do today before we take a break and play with the quiz is to specifically go back here. I want to make sure that everybody is able to apply basic calculus and apply it to physics. Because one of the questions on the test will be to ask you to really derive any of those equations. So make sure you understand those perfectly. So let me give you a short summary. Okay, Mabel. Soon, I hope. Excellent. So let's use, I'm just going to derive the first and second. Basic definition of kinematics are A is equal to dv dt and v is equal to dx dt. That's from those two definitions that all those equations of motion comes about. Oh, excellent, Mabel, excellent. So please read that lecture carefully, the equation of motion, because again, on the first test, one of the questions will be to ask you to rederive mathematically and precisely any one of those equations, either 1D or 2D. You will see that it's exactly the same. So if we pick a coordinate system such that y is positive up, then obviously we're concerned about the y direction. Therefore, this becomes y. Okay, let's start with the first one. If, again, my coordinate system is positive up, then obviously A is negative. I've changed the sign in my equations, right? So A is going to be negative G. Only because of the choice of the coordinate system. Again, if you chose positive y down, A will keep its positive sign. Therefore, we have A is equal to dv dt. Okay, so our stupid constant, negative, is equal to dx dy, same as you've done in calculus 1. Let's use that to derive the equation of motion of the velocity. I'm going to multiply both sides by dt, and therefore I have dv is equal to negative g dt. And I can integrate on both sides. So, you all know how to do this. No problem so far. This is where things are going to change in science versus math. We want the equation of motion. So, in math, what you usually do is you integrate this and usually add a constant. You call it C or K. And then you let the science people take care of it. Or sometimes, if you do the application, you're going to use initial condition to substitute for that value constant. In science, we do things a little bit differently. Since we want the equation of motion, and it's only because of this, we look at each variable. Let's look at the right one. It's a time, t. Remember, none of our equations have t naught. We always start our kinematic at t is equal to 0. So what goes in the bottom, or the lower bound of integration of the integral, are always the initial value. Since we're dealing with time, we start at t is equal to 0. On the left-hand side, since the dummy variable is velocity, this must refers to the initial velocity. And again, since we are after the equation of motion, we don't want to put values here. We need to put variables. That's the difference between science and mathematics. If you put constant and value, you're going to get a number, which is not what we want. We want the whole equation of motion. So this is where we're going to want to put the variables. Since the right-hand side is dt, we're going to put t. And since this is the velocity, dv, then we're going to put v. And this will give us the equation of motion. But before we continue, as you watch the lecture, you realize that, if you remember your calculus, this is an outrageous and a blasphemy from a math point of view. Because one of the bound of integration can never be the same as the dummy variable. You know from calculus 1 that every time you finish an integral, the dummy variable disappears. So they cannot be the same. So if we put the value of the variables on the top, or upper bound of integration, we have to change this little guy. So it's just notation, just to make mathematician happy. I'm just going to give it a different name. V prime, T prime. You can call it V1, T1, whatever you like. But now as we look at this equation, those are the most trivial integral ever. So that must be, the beginning of Calc 1, or the first time you see integral. This obviously is V minus V naught, because the integral is 1. And this is a stupid constant, which you can take out, because it's a constant. Therefore, you have t. So again, simple application of basic integration. And now we can solve for v. Now hopefully you do recognize this equation. That's the velocity as a function of time, which is consistent with this coordinate system. Again, if you had decided to pick positive y down, then you would have a positive right here. But that's the line equation. We just got this in its most general form, or this one. Okay? So that's where the power of calculus comes in. Very, very easy. Again, because we're doing freefall. We're going to revisit this as a situation where A is not going to be constant. That's going to be when we see drag. But again, the method is exactly the same. So that's the first step. We'll use basic definition of kinematics with respect to acceleration to obtain the functional form of the velocity. Now we're going to use the other guy, basic definition of velocity, in order to obtain the functional form for the position. Same technique. V is equal to dy dt. If you multiply both sides by dt, excuse me, then obviously v dt is equal to dy. Bang, let's integrate. Let's use the technique. The lower bound of integration refers to the initial value. If this is y on the right hand side, this must be y naught. If this is t on the left hand side, since we start everything at t is equal to 0, instead of putting t naught, we put 0. And on the top will be our variable itself, y and t. And again, since we can have both the demi variable and the upper bound being the same later, just change it. So again, same principle, same technique, just one line. The difference here is the right hand side is trivial. The integrand is 1, therefore we got 1 minus y naught. But the left hand side is quite different this time. V is not a constant. In general, V is a function of time. Therefore, we cannot just take it out. We need to know the functional form of V. And if V depends on time, we need to know its exact functional form before we can do the integration. But we just did it here. So it's easy. We just substitute this here. And therefore, we have V naught minus gt dt prime from 0 to t. And now we can integrate easily. Again, a polynomial, the most basic integration ever. This will give us v naught t, and this will give us 1/2 gt squared. And after you evaluate it between t and 0, the 0 terms will all disappear, and you look only left with this. You can move now the y naught on the other side, or was right on both steps. So now you can solve for y, and you end up with y naught plus v naught t minus 1/2 gt squared. Again, that should be this equation right here. Okay? So that's the power of calculus. Only using two basic definitions of kinematics. 1, 2. We can derive all those equations of motion that we've been using so far. But remember, the big thing that we've done is we assume that the acceleration was constant. So all those equations can only be used in free fall, or if the acceleration is constant. If the acceleration is not constant, then at this stage, right here, you're going to have to use some little tricks. If the acceleration depends on the position or on the velocity, etc., etc. So we're going to see a different situation in drag. But technically, you should be able to derive any equation of motion based on any value for the acceleration. And that's the reason why this is a calculus-based class and not a trig. In 151, we just memorize those 4 equations, and that's all we use. 170, now we realize where they come from. And therefore, on the test, I may ask you to derive the equation of motion. For example, if the acceleration is, I don't know, 3, like on the moon. And then you should be able to derive this equation of motion for the moon. Okay? So please pay attention to those lectures. You will have the exact same type of lectures for kinematic 2D, where similarly I've derived all the equation in the x and in the y direction. So Again, on the test, one of the questions will be asking you to derive those equations of motion. So I want to see this type of mathematics, basic application of calculus 1. And as you see, the integration is either a constant or a polynomial. So it's rather trivial. Okay? Questions on this? All right, so let's take a quick break. We're going to start with the first quiz after the break. It is a short one, just to get us, warm up. Oh, where, Brian? Can you grab the wand and point it to me after the 1/2 GT squared? Oh, this. Yeah. I'm sorry. It is indeed. Thank you. Let me clarify this. Oi. Oi. Up. So this is the same, and this is the result of the left-hand side. All right. So again, this quiz is very short, so you should be able to figure it out in like half an hour. If it takes you longer than half an hour, take your time. Make sure you master it, complete it. But this should be a waking call for you to realize that you're behind. So we may have another one on Wednesday on Kinematic 1D, or for sure next week on both Kinematic 1D or 2D. So there's only 2 questions plus a bunch of conceptual. So I'm going to put everybody in groups. It's the first time that I'm using this system, so let's see how that works. But the whole idea is that you talk to each other. That's why you have the mic. Hopefully you have a mic now. So please, talk to each other. You're always going to have the same quiz. I'm going to send it right after the break via email, so check your email right after the break. He's going to point you to a Google form, and you're going to be able to answer those questions. So please, as you work out the last 2 problems, or technically 4, work with each other. Use the board. Share your answer. Explain to each other so that by the end of this session, everybody is 100% on what to do, how to do it, and hopefully everybody has 3 points. Okay? All right, so I'm going to release the board. So now you should have a drop-down menu on the upper right corner of your window, which should allow you to go back to previous screens during the break. And then I will send a URL right after break. So 5:56, let's meet again in 6:06.